we know that aromatic rings are very stable. So you have benzene or phenyl rings, yet they can do some reactions under some conditions. So in this video, we're going to introduce how to add groups to a benzene ring or phenyl ring, and then how those things react. So let's just jump right in. First thing I want to show you is how to add a few groups to a benzene ring. Now these, I would just begin to memorize them. You want to have these down so you just can always grab them, put these groups on a benzene ring whenever you're ready. All right, so here's the first few that I would memorize. One, I can take a benzene ring and I can put a bromine on it, a bromide on it, by adding Br2 and FeBr3. Now bromine by itself isn't strong enough, so you need a Lewis acid like iron tribromide in order to get this to work. So the way I want you to think about this is that bromine, when it reacts with iron tribromide, think about this iron tribromide pulling off a Br minus to make a Br plus. And if you have a bromide that's a positive bromine, these double bonds that are in the benzene ring can come react with it to put a bromine on. So Br2 FeBr3 puts a bromine on. It doesn't have to be this Lewis acid, but with Br2, it's common to have FeBr3. To put a chlorine on, it's Cl2, and the Lewis acid is AlCl3. So Br2 FeBr3, Cl2 AlCl3. And to put an iodine on, it's I2 and nitric acid is what is used. So just start to memorize these. Maybe make some flashcards and put these in your head. But Br2, FeBr3, Cl2, AlCl3, iodine, and nitric acid. You should learn how to put a nitro group on a benzene ring. That's nitric and sulfuric acid. Nitric and sulfuric acid puts an NO2 group on. And one more, which we'll go into more in depth in a future video, is called the Friedel-Crafts reaction. And you can start putting alkyl groups on a benzene ring by taking whatever alkyl group you want, put a chlorine on it, a good leaving group, and react that with a Lewis acid like aluminum trichloride. So methyl chloride, aluminum trichloride. Again, think about these as pulling off the Cl minus, and making a positive methyl, and then that can react with the benzene. All right, now once you have those five in your mind, all of those, you had to make something very positive in order for this stable electrons to come react. We won't get into the mechanism of this, but those electrons, it breaks the aromaticity, reacts with something, and then you reform the aromatic ring. So we have five reactions. Br2 FeBr3 puts a bromine on. Cl2 AlCl3 puts a chlorine on. I2 nitric acid, iodine. Nitric and sulfuric acid, NO2, nitros. And finally, Friedel-Crafts, some alkyl chloride and aluminum trichloride. And that has a lot of little things that you have to learn about it, but that's the basic idea how to put a methyl group on. Okay, now, once those groups go on, here's something else I need to think about. If I take a benzene and I react that with nitric and sulfuric acid and I make a nitrobenzene, I can put that group on. But what if I start with something like a methyl group on my benzene? We call that toluene, this methyl benzene. I do the same reaction. I'm adding nitric sulfuric acid, so I'm going to put an NO2 group on. Now that NO2 group, if I just put one on, can go three different places. It could go right next door and make ortho. It could go two away and make meta. Or it could go, three away, so on the opposite sides, 1, 4, and make para. So I can make ortho nitrotoluene, meta nitrotoluene, or para nitrotoluene. When we do this reaction, we find that we don't make much of the meta. We tend to make the ortho or the para. So we say that this is an ortho-para directing group. A group like a methyl directs what's going to come on next in the ortho positions and the para positions. Those are the ones that we get. So methyl groups are ortho-para directing. You can see you're going to use some brain power here. So now I know that that methyl group directs ortho and para. But why? So let's take a look at the mechanism for when the nitro group comes on the toluene, and that'll help us understand a little bit more about why it's ortho pair directing. So let's say this nitro group comes on ortho. If it comes on ortho, it comes on here. If it comes on meta to it, that's this line. And if it comes on para to it, that's this line. So if these electrons go and grab the NO2 group, this actually makes NO2 plus. If those electrons grab that, these are the intermediates we make. So those electrons go to make a carbocation here. I can draw resonance forms around that ring and put the positive 3 different places. I want you to notice this carbocation is tertiary, this one's secondary, and this one is secondary. This carbocation is secondary, this one's secondary. That means it's only got 2 things attached to the carbocation. And this one is secondary, only has 2 carbons on the positive charge. This one has 2 carbons on it, secondary. This one has 1, 2, 3 carbons on it, it's tertiary. And this one only has 2, it's secondary. So I want you to notice that this one is tertiary, and tertiary carbocations are more stable than secondary. This one is tertiary. So if I do ortho or I do para, I make something that's a little more stable. But if it goes on meta, they're all secondary, which is okay, but it's not as good as tertiary carbocations. So that way, if I have a methyl group, we like to stabilize that positive charge. So by making these tertiary carbocations, so the group goes on ortho or it goes on para, but not meta. And that's why you get these. So I want you to remember that this group is right next to that positive charge. So what if it's a different type of group? What types of groups help that positive charge, and what types of groups would hurt that positive charge? So I'm going to take this one right here, and I'm going to show you 3 different scenarios if it goes on ortho. There's one more thing we should talk about when it comes to these. When I had a methyl group, since it donated some electron density into the ring, there's more electron density in this ring. So compared to benzene, with a methyl group on, it reacts 25 times faster than it does just benzene. Methyl makes it go faster. So we say the ring is activated, or this methyl group is an activating group because it makes the reaction go faster. The methoxy, because it donates electrons in through resonance, really adds electron density to the ring. It's so good. These are both ortho pair directors. But this makes the ring so reactive, it reacts 10,000 times faster. We say it's really activated, so it's also activated. So methyl, methoxy, anything with a lone pair of electrons on it, nitrogen, sulfur, those things make it activated and make it react faster. The nitro, things that suck electron density away from the ring, electron withdrawing groups we call them, make it react slower. This reacts with a nitro on the benzene. It makes it react something like 100,000 times slower than just benzene. So we say the ring is deactivated. It reacts much slower than it does if it's only benzene. So electron donating groups are activated rings. They react faster. They're ortho para directors. Deactivated groups, like nitro groups, are meta directors, and they make the reactions go slower. So let's look at some examples. So if I start with nitrobenzene, and I react with chlorine and aluminum chloride. First, I think this reaction might proceed a little slower, because this is a deactivating group. But the nitro group, it donates, or it directs, the group that's going to come on to the meta position. So let's see, if this position's here, this is the meta positions. So I'm going to add chlorine, because that's what Cl2 and aluminum chloride do. So my nitrobenzene will add a chlorine, because I'm using these reagents, to the meta position. How about this one? So this toluene, methylbenzene, is going to add bromine, because that's what Br2 and FeBr3 do. This is an activating group. It directs to the ortho and para positions. So these are the ortho and para positions. So I'd expect to get, let's see, I'm putting bromine on. Ortho. And para to this. In this case, I'm going to put a nitro group on, NO2. So let's see, this methoxy, because it donates electrons in to the ring, directs the group to the ortho or para positions compared to that. I'm going to put on an NO2, so I'll put it ortho. And I'll put it para. Now, because there's two ortho positions, I might get more of these than I do of the para. That's okay. I just want you to realize now that you'll get ortho and para. So we see that groups that are ortho-para directing and activating tend to be like methyl, ethyl, different alkyl groups, phenyl, anything that's an alkyl group. Lone pairs of electrons on things like oxygen, so ethers or alcohols or amines, lone pairs on nitrogens, or negative oxygens, even like oxides. Those all donate electrons in ortho-para directing activating groups. We've seen that nitro is a meta-director. It's deactivating because I'm pulling electrons out of the ring. So nitro does that with this positive charge in the N double bond O. But things like carbonyls do that. They pull electrons out of the ring. So it's less electrons in here. It'll react slower. It's deactivated. Sulfonyl groups, S double bond O. Nitriles, I can pull the electrons all the way up to the nitrogen. Things with positive charges on it would be very deactivating. So these are deactivating. They go slower than benzene, and they're meta-directors. Now, how about something like fluorine? I think there's two things going on in fluorine which might make it kind of confusing. You might think fluorine, I remember fluorine. Fluorine is very electronegative. It sucks electrons towards it. So if I'm sucking electron density out of the ring, will this ring react faster or slower? Of course, it's going to react slower. So we say it's deactivating. It'll go slower, just like nitro or carbonyl. But you may have also noticed something like a fluorine has lone pairs of electrons on it. So they can donate the electrons in much like these can. So that makes it ortho-para directing. So halides, they end up reacting slower, so they're kind of a mix of both. I remember things like halides suck electrons out, so they're deactivating, but the lone pair makes it ortho-para directing. So it's kind of a mixture of these, deactivating and ortho-para directing. So that would mean fluorine, chlorine, right, bromine, any of the halides, iodine, they're all going to react slowly, but they'll be ortho-para directing. All right, let's put these all in a list. So it may help you to see the list like this. Things like nitro, carbonyl, S double bond O, nitriles, positive charges, all of these things were deactivating. Fluorine, chlorine, bromine, iodine, these are electronegative things. So all of these are deactivating. They all pull electrons away from the ring and make it react slower. These things donate electrons into the ring, so they'll make the ring react faster. These are activating groups. So methyl, ethyl, propyl, phenyl, the alkyl groups. The lone pair things are even more electron donating, right? These donate electrons in. So these are even stronger than the phenols or the alkyl groups. This is also pretty good, amide, but I drew it kind of in between. It's not as good as these. Here's why. Even though if the ring is here, these can donate electrons into the ring, so that's good. But I can also draw a resonance form where I can draw them up to that oxygen. So they're pulled away from the nitrogen a little bit as well. So they're not fully available to be donated in like these are. So it's kind of in between. But all of these are activating. And, even more so than this would be something like if I had a negative charge on it, that's really going to be donating in. That's going to be very activating. So all of these are ortho para directors. They'll direct the group ortho or para to it. So because of the lone pairs, these are ortho para directors. All my halides are. These alkyl groups are donating electron density in through hyperconjugation, and of course the lone pairs. All of these withdrawing groups that are deactivating are meta directors. So I'm looking for that double bond O thing, triple bond N, where I can pull the electrons away, N double bond O, S double bond O, positive nitrogen, meta directors, and deactivating groups. And the halides are the ones that are a little bit mixed of both. They pull electrons away, and they're ortho para directors. All right, let's just practice a few problems now. Let's see if we can predict the products of these reactions. So I have ethylbenzene, so I'll draw my ethyl. This chlorine aluminum chloride will put chlorine on. Where will it go? Well, let's see. My alkyl group, my ethyl, that's a donating group. It's ortho para directing. So here are my ortho spots to that ethyl, and here's the para spot to the ethyl. So if I draw it, I'm going to expect to put a chlorine on here. I'll draw this one, the other spot, but these are equivalent, right? So you don't usually need to draw both of those. And the para spot. So I'm putting chlorine on because I use that reagent. This one, I'm starting with benzaldehyde. My carbonyl on there. This means I'll put an NO2 group, nitric and sulfuric acid. Nitrates puts NO2 on. So where does the NO2 go on? Let's see. This has the carbonyl, so I'm pulling the electrons away from the ring, right, up to that oxygen. So it's a meta director. So that means it'll go meta. And I'm putting NO2 on. You can draw the other meta position, but you don't need to. All right, let's take a look at this one. I have ethoxy. So OCH2, CH3. Let's see, where does that direct? Well, I have lone pairs of electrons that can push in. So that's very activating, ortho para directing. So ortho to that spot or para to that spot. What do I put on there? Well, Br2 FeBr3 puts a bromine on. So we'll put bromine on, ortho, and para. And again, I could put the other ortho one, but it's the same as this, just flipped over. Here's a few more. Let's see, C triple bond N. I'm pulling the electrons away. They can go up to the nitrogen. So that's deactivating meta director. So meta to this, ortho meta would be those positions. What am I going to put there? Iodine and nitric acid puts an iodine there. Isopropylbenzene. Let's see, that's an alkyl group, so that's an ortho para director. So I'm going to add chlorine because it's Cl2AlCl3. So the ortho position and the para position. You could draw the other ortho position. It's the same thing as this, just flipped over. Bromobenzene. Let's see, halides. They suck electrons away, so it'll be slow, deactivated. But there's lone pairs of electrons that could donate in. That reminds me they're ortho and para. So ortho and para to that position. And I'm going to add nitric sulfuric, so that makes a nitrate. A nitro compound, so ortho and para. Here I have a benzene ring. Let's see. Now don't let this carbonyl fool you. Just because there's a carbonyl doesn't mean it's going to go meta. because right here I have a lone pair. The atom that's attached to the benzene is a lone pair of electrons on a nitrogen. That can donate in. So that makes it ortho and para. So ortho spots, my para spot. So I can put a group here. And a group here. What do I put on? I guess it's going to be chlorine in this case. So that's how you do those. Let's show you one more thing that you might encounter. What if there are two groups on the benzene ring? How do they direct? So let's look at 3 examples, work through them, and you'll see how to handle these. All right, so this case, I have an ethyl group. It's an ortho-para director. So let me circle the ortho spots to that and the para spots to that. Here I have a methyl group. That's also ortho and para. So let's use red. So that locates this spot, or is ortho to it. This one's ortho to it, and this one's para to it. So they both point to the same 3 locations. I'm going to add my nitro group because I'm using nitric and sulfuric acid. So I'd expect nitro here. I'd expect nitro here. And I expect nitro here. And maybe if I had to guess, I might think I get a little bit less of this one because it's kind of crowded and I have to squeeze it in between these 2 alkyl groups. So I expect I'm probably not going to get as much of that one as I would putting it on the outside of those spots. Let's look at this one. Here's 2 groups. Again, I'm going to put a nitro on, but where do I put the nitro? Well, this group up here is methoxy. It's donating electrons in. So that's ortho para, very activating. So there's the ortho spots. Para spot, there's already something there. I can't put it there. Then we look at this one. It's a carbonyl. That's a meta director. So meta to that would be here. Ortho meta to this group. Meta would be here. Ah, they all point in the same direction, same location. So I'm going to put my nitro in that location. You can put it either side. How about this one? So methoxy donates in, ortho or para to that. So here, here's ortho, and there's para to it. Here's my nitro group. Where does it point? See, nitro's meta directing. So there's my ortho. This meta already has something on it. Here's the meta spot. Here's our first example where they point to different locations. So where is this nitro group going to go that I'm going to put on? The blue ortho para spots to this one, or this red meta to this one? Well, let's see if we can think through this. This one is a deactivating group. It reacts very slowly at that meta position, but it will direct it there if it has to. This reacts very fast because it's activating. So these spots react very fast, while this one reacts slow. So it'll direct it to the blue spots more than that red spot. So if I draw my product, we'll put the NO2 group on that spot. So it goes here, here, and here. So those are the locations. I expect this one, squeezing it in between, to probably not happen as much as putting it more on the outside spots. But whenever you have 2 conflicting things, you go with the more activating spots. I hope that was helpful. That's just an introduction to aromatic reactions. There are many more to go through, but my recommendation is learn those 5 reactions right away, so you spend all of your brain power on the directing. Is it ortho and para? Is it meta? Those sorts of things come next. Hey, subscribe to the channel so I can continue to help you with your organic chemistry.